Okay, this is integrated to section 2.2.1, talk a little bit about dilations. So previously when you guys did transformations last year, and probably in Math 8 too as well, I believe that you guys went through and you did rotations, reflections, and translations. Those are rigid transformations. So what that means is that as we move something around by reflecting it or translating it or rotating it, it preserves the original shape and the original size of the object. A dilation is a non-rigid transformation, which means we're going to be taking a shape and we're going to be blowing it up so it's much larger, or we're going to be shrinking it down so it's much smaller. And maybe even like a tiny bit smaller or a tiny bit larger. So we're going to be talking about that today. So hopefully at this point you have already watched the pantograph that you should have watched before this. We would have been building these in class. Unfortunately, we aren't. So hopefully we can go through and create some sort of a decent facsimile of what we would be doing in the classroom. So at this point, I want to be able to take this diagram and I want to dilate it by a factor of 2, and I need to do it from the origin. So if we were creating this in class, we would have sets of 2 rubber bands tied together at once. So that would be our factor of 2. And what we want to do is kind of affix that rubber band. So one of the rubber bands based at 0, 0, the origin. And then what we would do is we would stretch that rubber band so that the only knot that we have would sit on the periphery or the perimeter of our shape. And then we would be tracing it with our pencil and the other rubber band, trying to keep the knot as close to on the shape as possible. So I want to think about drawing some line segments to help myself out here. So if I'm trying to get to A, I know that I would have my rubber band kind of stretched out over to point A. Now, that's where my knot would be sitting. Now, we would have used rubber bands of the exact same size, so that's important to note here. And then if you take a look at the pantograph video, the rubber bands themselves, when tied together with the pencil on the end, are actually forming a line. So I think we can use the idea of slope to help us out here. So if I take a look at this triangle here that I just created, kind of like a slope triangle, I know that that would have a rise of 2 and a run of 3. So I'm going to go ahead and do that again. So right here at A would be where my knot is located. But then I would still have one more rubber band that would have been stretched out the same amount. So there's my rubber band, my dashed line. So I think at this ending point, this is where my pencil would be located, right there. So I'm going to call that my new location of A. And just like last year, we would always call the movement or the change of an original location to a new location as A prime. Okay, I want to do the same thing with the other ones. So I'm going to take every corner and I'm going to stretch my rubber band out there. Now I'm using the corners because it's a little bit easier to see the stretch. Now understand, if we were doing this in class, you would actually be keeping the knot along the shape itself. So we would be going along this shape from A to B. So that would be our goal. But since none of those, well, maybe one of them is a lattice point, it's a little bit harder to look at. So we're going to take a look at the corners themselves. Okay, so if I take a look at this, I'm still going to use that slope triangle. So I see that it is down to right 1. That is where my first rubber band would be located, or the first knot. So then I'm going to go ahead and stretch it down to, again, and right 1. So here, this dashed line is where my rubber band would be located. So this is where D prime would now be located. So we want to go ahead and do the same thing with all of the other corners. So if I take my rubber band to point C, then it looks like that's going to be down 2 and left 2. So that's where the knot would be located. So let's go down 2 and left 2. That is where the end of my rubber band would be located, where my pencil would be affixed. And there's my rubber band. So this would be C prime. And then likewise, we can do the very last corner here. So it looks like, again, I keep coming from the origin, and that's because that's the point of dilation. So I would be up 2 and left 1. So that's where the knot would be located, and the dashed line is where my rubber band would be. Okay, so my rubber band would still be stretched in the same direction for the same amount. So that point is where my pencil would be. So now the last thing that we need to do is to go ahead and connect those dots. So this thing's going to look like a rainbow. Let's go ahead and use red to connect. So A prime to B prime, A prime to D prime, D prime back to C prime, and B prime to C prime. So the red shape that we have, which we can make a little bit thicker so it's a little bit easier to see, the red shape would be our dilation of the original shape from the origin by a factor of 2. Okay, on the next slide, we want to do the exact same thing, but we're going to dilate it by a factor of 3, still from the origin. So you want to do the same process that we just did. If we were in class, we would have had 3 rubber bands tied together, which means we would have had 2 knots. So there would be 2 knots, and then where the pencil is located as we're tracing. Why don't you see if you can go ahead and graph this one? Okay, so what I did here was I got rid of the slope triangles because the first one looked a little crazy and this one would look worse. But what I did do is I still put the dashed lines where my rubber bands would be located. Additionally, for example, if you take a look at the purple marks here, the purple marks for A, all of the big dots that I put on, those would be representations of where the knots would be located if I was using my rubber bands for this. So go ahead and check your answer against mine. And then I believe on the next slide we have another one that we're going to be doing, but we're going to be using a different point of dilation. So it doesn't always have to look like it's kind of blowing up from the middle, which this one looks like that. Kind of looks like it's blowing up from the middle, just because the origin is inside the shape itself. But your point of dilation does not have to be inside the shape. It could be outside. Okay, so let's take a look at diagram number 2, and we're going to dilate this by a factor of 3 from the point of dilation. Well, notice that the point of dilation is on the outside, so it's right there. But the process is the same. So I want to imagine having my rubber bands tied together, and it's a dilation of 3, so I would have 3 rubber bands tied together, which means I would have 2 knots. So if I kept the end of one rubber band affixed to point D, and I actually drew out the rubber band being stretched, then the first knot, just like the previous object, would land right on top of the point. I'm still going to do slope for this, but it's from the point D, just kind of like the origin was before. So it looks like this one is up 2, right 2. So I'm going to do that again. So I'm going to go up 2, right 2, and I'm going to plot that point fairly large because that's where another one of the knots would have been located. And I'll go ahead and mimic my rubber band. Okay, but if you take a look at that, we see these sections. So this stretched part here, that represents, so my dashed lines represent my rubber bands themselves. So at this point, I only have 2 of them, which means I need 1 more. So I'm going to do the same thing. So I'm going to use the slope again, so up 2, right 2, and that is where my pencil would be located. So that's where I am at the end, and you can see my 3 rubber bands. So there's 1, there's 2, and then there's the third one. And then where each one of those are meeting is where the knots are located. So at this point, I think we know where F prime is going to be. So F prime is going to be there. And we want to do the same thing with the other corners. So if I take a look, and I want to go from D to H. If I counted this correctly, it looks like it is up 3 and right 9. So up 3 and right 9. So here's my rubber band coming through. And my first knot is going to stay at H. So we want to mimic those rubber bands again. So see if you can figure out where the rubber band ends or where your pencil would be located for H. So it looks like H prime is pretty far out there, which makes sense. So I have the location for my first rubber band, or the knot, is at H. Then the next rubber band is at another gigantic green dot. So each one of these sections, again, that is dashed, represents my stretched rubber band, whereas the dots represent where the knots were located, or at the very, very, very end where my pencil was located. Okay, now the next one looks a little odd just because there is no up-down motion. It's just right and left, but it's the same idea. So we go ahead and count the boxes over. So it looks like it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's my rubber band. And then that's where the first knot would land. Let's go ahead and do the other two. Okay, so I've got my rubber bands all stretched out. So my first rubber band would be there, and then the knot, my second rubber band, then the knot, and then my third rubber band and where my pencil would land. So I think what I want to do at this point now is just connect my new location. So my F prime, my G prime, and my H prime. So if I connect F and H, and I connect H and G, and then the last one, F and G. So there's our new dilated shape for this one. Notice the larger the dilation, the more room you're going to need. And then it doesn't always have to be right around the origin. It does just kind of look like it's been like blasted out from the shape though. Okay, so here we go. This is our last question. So we want to take a look at these and we want to try to figure out which ones are similar. So what I did, and I thought this might be a little bit helpful since we're not in the classroom together, was I went through and I traced a couple of the shapes. So what I want to be able to do, we know that for shapes to be similar, they have, their angles still match. So the angles don't change. But we do have a ratio that separates the side lengths. But what's really nice about being able to prove similarity, and we're going to get into full-blown proofs later this chapter, is that if we can prove or show that the angles match, then it is necessarily true that the side lengths will have a common ratio. So what I'm going to do with my traced little objects, and I've got this object A that I've traced. So I'm going to go ahead and grab this, and I'm going to try to move it around my pictures. Ideally, I want to see if I can get all the angles to match up. So what I could do if I would want to is I can actually enlarge this shape, or I can leave it the size that it is. It doesn't matter because the angles are going to be preserved the entire time. So I think I'm going to leave it at what looks like a manageable size to me. And then I'm going to go ahead and drag this around. So I want to see if the angles are going to match. Okay, so that angle looks like it matches. I move around my shape. I want to make sure that the corners match up, which this one looks like it's good. So I would say that A and C are similar to each other. Let's take a look at B. Oh, B's looking promising. And kind of slide my shape around here. And all right, B's good. All right, let's check D. Well, D's a little bit smaller. So let's see if we can shrink our A that we're using. Let's go ahead and put this in here. Uh-oh. It's close, but I don't think that those match up. Notice that the angles are just off by a tiny, tiny bit. So I'm thinking for this one that I would say yes to A, B, and C, and I would say no to shape D. So I would cross that one out. So that one's not going to be similar. And we want to go ahead and try it again with part B. Now, I would do the exact same thing. Remember, you can kind of grab this and hopefully move it around. Now, you may need to rotate it a little bit, which is fine as well. So if I get this to rotate, I can enlarge it and I can shrink it. And I'm going to move this around. Now, the only thing that's hard with using the program that I'm using is that it's difficult to reflect it. So I think I'm just going to kind of play around with it by moving it around a little bit, by reflecting and by rotating and translating. This one looks pretty good. So I think B and D are going to match up. So what I recommend that you do is go through, double check these. Okay, so that one looks good. That angle matches also. And then see if we can get the angles that are going to match up. Notice that I am enlarging my shape and shrinking it, and the angles aren't having a problem. So let's see about this guy. Uh-oh. I don't think that one works. All right, let's see about any other ones. Nope. Okay, I think C is a problem. So C doesn't look like it's matching. All right. So one of the other things that you can do while you're working on this yourself is take out a sheet of patty paper or a sheet of tracing paper, or your parents might have some of the tissue paper around the house for when they wrap presents, and you can use that. Or you can take one of these shapes, you can cut them out and then rotate it and reflect it yourself. You don't have to worry so much about the side lengths. It's really about the angles. If you can get the angles to match, then you're good. And that covers dilations.